Hello, this is Dr. Holcomb. In this video, we'll be discussing the E2 mechanism, a stereospecific elimination reaction. The dehydrohalogenation of alkyl halides gives alkenes, but different conditions give different results. Consider the dehydrohalogenation of compound number 1 in methanol with heat. The major product is the tetrasubstituted alkene compound 2. In this reaction, loss of a bromide to form the carbocation, followed by removal of the proton from the carbon bearing the fewest protons, gives rise to the alkene, according to Zaitsev's rule. It is therefore an E1 elimination reaction whose rate law is unimolecular. Product formation is governed by thermodynamics, thus giving rise to the tetrasubstituted alkene. In contrast, treating the same substrate with a strong base in methanol leads to a very different outcome. Here, treatment with a strong base in the absence of heat gives rise to the less thermodynamically stable trisubstituted alkene compound number 3. Furthermore, kinetic studies indicate that the rate-determining step for this reaction is bimolecular. Before we consider the mechanism to explain this unexpected product and the bimolecular rate, you should ask yourself, what would you do first to better understand this reaction? If you said, draw the cyclohexane chair conformation, you'd be right. Let's begin by looking more closely at the E1 elimination reaction. In this reaction, heat promotes the loss of the bromide in the rate-determining step to give the carbocation. The carbon of the carbocation is sp2 hybridized, trigonal planar, and has an empty p lobe that is roughly collinear with the carbon-hydrogen bond of the hydrogen that's eliminated. Elimination of this proton in a fast step gives the thermodynamic tetrasubstituted alkene. However, this is not the only conformer present. Furthermore, there are two additional beta hydrogens. It is this conformer and these beta hydrogens that we must consider when we explore the mechanism that gives rise to the less thermodynamic product. The product distribution suggests that we must consider the role of the alternative beta hydrogens in the elimination reaction. Furthermore, the bimolecular rate law indicates that there are two species involved in the rate-determining step. Combining these observations suggests that it is the axial beta proton that is removed in a concerted process that eliminates the axial bromide. This bond breaking and bond forming is the slow step and therefore the rate determining step. The reaction involves a strong base, is bimolecular, and designated an E2 elimination reaction. The E2 elimination reaction is stereospecific, and the proton that's abstracted is collinear or antiperiplanar to the leaving group. A view down the axis of the two carbons involved in the alkene formation affords a Newman projection. In this Newman projection, we clearly see the anti-orientation of the proton abstracted and the leaving group. The hallmarks, then, of an elimination reaction are a strong base whose nucleophilicity is often attenuated, in this case, by a protic solvent. The transition state occurs through an elimination of a beta proton that is antiperiplanar to the leaving group. We can clearly see the collinear alignment of the beta proton being abstracted and the bromide leaving group in the Newman projection. Given that the E2 elimination reaction is stereospecific, different stereoisomeric starting materials should give stereoisomeric products. And in fact, diastereomeric starting materials give rise to different products. The two geometric isomers are formed as a consequence of the mechanism of the E2 stereospecific elimination. Let's begin our analysis by constructing a Newman projection of the SS stereoisomer. For the conformer shown, the beta hydrogen is not anti to the bromide. A rotation about the sigma bond is required to provide a conformer that will undergo E2 elimination. Once the anti-periplanar orientation is obtained, elimination can proceed. As the double bond is formed, the two phenyl groups will align on one side of the double bond, and the methyl and the hydrogen will align on the other side. This alignment down the axis of the double bond corresponds to the Z isomer as shown. One can also view the rotation about the sigma bond using zigzag structures. We rotate the sigma bond so that the beta proton and the bromide leaving group are collinear in the plane of the paper. Stereospecific elimination affords the alkene. The two phenyl substituents are cis, while the methyl and the hydrogen are on the opposite face of the alkene. Let's perform the same analysis on the RS isomer in which the bromide stereochemistry is inverted. We perform a rotation to give the conformer in which the beta proton is antiperiplanar to the leaving group. In this case, alkene formation places the phenyl and the hydrogen on one face of the alkene. The methyl and the other phenyl are on the opposite face. This E-alkene is formed stereospecifically from the RS diastereomer. E2 elimination reactions may also be conducted in polar aprotic solvents using bulky bases. With a bulky base like T-butoxide, elimination occurs at a faster rate than SN2 substitution. Concerted elimination gives rise to a bimolecular transition state. The rate of product formation is then governed solely by the transition state energy. There is no carbocation intermediate, as with E1 elimination reactions. Consequently, under E2 elimination conditions, one does not see migration products. With E2 elimination conditions, then, one can avoid the mixtures that sometimes arise with E1 conditions. Now let's use our understanding of the stereoelectronics of the E2 elimination reaction to determine which of these two stereoisomers reacts faster. We'll begin by drawing the lowest energy conformer of each isomer in which the methyl groups are equatorial. For isomer number 1, we see that the bromine is anti-periplanar to a beta hydrogen. For the low energy conformer of isomer number 2, we see that the bromine is not anti to any of the beta hydrogens. This is highlighted by the Newman projections. Again, the most stable conformer of isomer 1 places the beta hydrogen and the bromide leaving group anti, whereas in isomer number 2, the low energy conformation places the hydrogens and the bromine gauche. The stable isomer of conformer number 2 will therefore not undergo an E2 elimination. Because there are no beta protons anti to the bromide, a ring flip must occur. Only after conformational change to the less stable conformer can elimination occur. The rate of reaction of compound 2 is therefore slower because of the higher energy of the transition state of the E2 elimination. Now it's your turn. Use the same analysis to determine which of these two isomers reacts faster. Press the pause button now and work it out on a separate piece of paper. Your first step in this process should be to draw the chair conformation of both isomers in which the isopropyl group is equatorial. For compound 1, this low energy conformation places the bromide in an equatorial position. A ring flip to a higher energy conformer resulting in a higher energy transition state slows the rate of this reaction. For compound 2, the low energy conformer places the bromine in an axial orientation. The transition state of elimination is therefore lower and the rate is therefore faster. Both reactions give the same product, but compound 2 does so at a much faster rate. So the stereoelectronics of the E2 reaction can greatly affect the rate of reaction as well as the product distribution. Pause the video now and work out for yourself the products of these two reactions. In the first case, the low energy conformation leads to the more highly substituted Zaitsev product. In the second case, the equatorial bromide cannot undergo an E2 elimination. A conformational change is required in which the bromide becomes axial. E2 elimination of the axial bromide gives rise to the disubstituted alkene. In general, then, for cyclohexanes, E2 elimination occurs with axial leaving groups. What about acyclic alkyl halides then? Pause the video now and work out which geometric isomers result from the following stereoisomers. To solve this problem, I drew the appropriate conformer for each isomer. I then identified which groups would end up on which face of the alkene. This gave me the Z and the E alkenes, respectively, from each given isomer. Understanding the stereoelectronics and stereospecificity of the E2 elimination reaction is essential for predicting the products of elimination with a strong base.